Recording. All right, we're going to talk about atoms and elements. Like I said, we're going to talk about in lab this afternoon. We will finish up the lecture for chapter 3. For now, we're going to try to get through chapter 4. This is a little bit less of a dense subject, but there's still a lot of material in it. Okay, it's a lot of memorizing in this chapter. Okay, so he wrote this in the book. He talks about the experiences in atoms at Tiburon. Basically, the simple answer is everything that you smell, touch, feel is made up of atoms. Okay, so what we're going to talk about in this chapter is atoms and some molecule stuff. Okay, so atoms are the smallest identifiable unit of an element. Okay, what does that mean? Well, some elements don't come as individual atoms. They come as molecules. Okay? So, for example, I'm just going to tell you up front, oxygen is O2. It's known as a diatomic element. But the smallest unit of oxygen, like oxygen O2, is actually just O. Okay? One of the really cool ones, should I tell you about the really, really cool one or just the cool one?
What about quarks?
Quartz?
Quarks.
Quarks? Quarks, yeah. So those are the things that make up the subatomic particles within atoms. So everything is kind of, actually, if you want to get like deep into it, is made up of quarks and muons and all these things. But the stable pieces that we see, the things that will just sit around essentially forever, are the atoms. Those other particles that you're thinking about, all the subatomic particles, they combine to make those particles. But they don't themselves never like exist for a long time.
This is like the unit that can do something.
Yeah. So, all right. So smallest identifiable. So you want the really cool or the really cool? Really cool is phosphorus. Phosphorus is P4. And I've had my suspicions about this for a long time. There's actually two kinds of phosphorus. There's red and there's white. But they're both just phosphorus atoms. 4 of them combined together in a molecule. When they originally discovered, there's a guy named Brandt, I think it was Brandt was his name. When they originally discovered phosphorus, this was about the time of alchemy. They were trying to isolate all the essential things, and they thought everything was colors and smells and textures, and so they were trying to isolate different elements, but to them, elements were like the colors, okay? So what they did is they took a bunch of sailor pea. Okay, this is 1600s. A bunch of sailor pea, like 50 gallons of it in a bucket, and then the bucket after bucket after bucket, stuck it under a house. Now, I don't know why you do this, but you stick it under your house and you wait for it to start to grow worms. And then you boil it down. This has got to smell horrible. Would you imagine 50 buckets of pea underneath your house? Gallons, like big buckets. Sailor pea, though. I love the details. And then I always think to myself, this is going to help you remember the symbol for phosphorus, because what is it? It's P. I don't think that's why they did it, but that's what it is, right? And so when they boiled it all down, okay, eventually it began to glow. And that glowing is what we call phosphorescence. And you know, when you're an alchemist and you've discovered something that glows on its own, you think you're the cat's something. I don't know whatever the cat has, but the cat's thing. Yeah. So anyways, that's the really, really cool one. But there's actually 2 kinds of phosphorus. There's red and there's white. And if you remember the old match heads that were self-igniting, that you could just strike it on a wall and it would light, if you remember those, that white top is white phosphorus. And you could ignite it by just striking it. It would catch on fire. It's so unstable. Anyways, P. Love talking about these things. Hi, sorry, I was just talking about P. What are you up to?
We're from the tutorial center. We wondered if we could give a presentation or if we should come back another time.
Now is good. All right, so there are about 91 different elements. Okay, so this is what I would like you to memorize. So I'm recording this, so it is very clear what I'm asking you to do. Okay, so here we're at the periodic table. And I'm going to write it on the screen too, but I can write on the screen and talk from here. You need to know the names and symbols. Oops. Okay. I usually do the first 4 periods of the periodic table. First 4 rows. So what is that, right? It's starting with hydrogen. What is He? Helium. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Now, if you're going to go into biochemistry and biology, this whole block right here is really important to you. You need to know all those. But all the way down through potassium, calcium, scandium is a little weird, but you know titanium, vanadium's a little weird. There's chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine. Anyways, it's in your book. Okay? That's what I want you to know. Now, there's a few others that I want you to know. So let me list those out. There's silver. That's Ag. Cadmium. Next to silver, Cd. A lot of them end in IUM. I don't know why in chemistry. Now, these ones you should know for sure. Platinum, gold, mercury, and lead. What do you think platinum is? PT? Yep, gold is AU. It's like, hey, you. So PT, AU. Mercury is Hg. And lead is Pb. Now, there's a bunch of others, and you're going to learn them. Lead is one of the weird ones, though, right? Because lead isn't Pb. In Latin, it's plumbus, and that's where it comes from.
I was just wondering, when you test us on these, are you just going to have us, like, for memory, just write every single one in its term, or are you going to have like a bank?
Oh yeah, so yeah, I'll have like a symbol, give me the name, give me the symbol. So you'll have one of them, and you just have to give me the other, or I'll do a multiple choice. Right, I'll say, which of the following is potassium? Of course, I'll put P there because that's phosphorus, and that's what everybody wants to answer. I'll put K there because it's potassium. K is potassium. By the way, it's really funny because I've had Russian students that were like, oh yeah, of course it's K, because it's kalium. They know that in Russian. That's how it's taught to them already. Okay, so yeah, so I'll put a couple other weirdos in there, but that's the idea. You'll have to get it on a multiple choice, or you'll have to just write one or the other. Spelling will matter some, okay, so make sure you can spell them, but most of them you should know how to spell because they're pretty common. Like, you know how to spell calcium, you know how to spell, I don't know, hydrogen, I hope, helium, neon, like neon signs, N-E-O-N. I mean, I'm a horrible speller. You'll see it as I write up here. You'll be like, that's not the way you spell that, Dr. K, and I'll be like, meh. Sorry. I try to get it right. All right. Okay, so they're very small, just give you a scale. They are on the order of, and they're all different sizes. By the way, the ones at the top are the smallest, the ones at the bottom are the biggest. Kind of makes sense. They're done in kind of in order, right? The smallest to biggest, though, average size, let's say, is about 0.1 nanometers, like a tenth of a billionth of a meter. It's a really tiny, tiny thing, okay? Just a thought, like if every atom within a small pebble were, like if you took one of these and you took every atom, right, you made it the size of a pebble, it would be as big as Mount Everest. That's how many atoms there are in there. Okay, so atoms are really small. That's the important part. Let's talk a little bit about atomic theory. Like, how did we get the idea of atoms? And it turns out really early on, and the guy we usually attribute a lot of this stuff to is Democritus. And in philosophy, the person who argues the best would win. They thought all of nature should be logical, and you should be able to logic your way through the natural sciences. So Democritus actually came up with the idea of atoms and individual units. He was a little bit of an alchemist too, they all were. So they were thinking like the smallest units might be a unit of color or something like that, right? But he had the idea of simplest, smallest bits that could combine with other things to make molecules. Well, he lost because he couldn't logic his way out of it because they didn't do experiments. They believed you should be able to rationalize everything. Since he didn't want to do an experiment, he lost. The argument was then everything became continuous, and there is no smallest unit. And we did that for 1,000 years, right? 2,000 years. 2,500 years ago. Well, and so Democritus called them atoms, right? Atmos, because they're indivisible. They're the smallest unit of matter. Now, we know, modern era, nuclear, right? You can split an atom. It's not the smallest unit. And we know about the subatomic particles, and we know about the quarks and all those things, the mesons and all these things that make them up. Muons, I should say. Anyways. Then, about 1808, started a little bit before that, a guy named John Dalton came around. He's from Manchester, England. You can still go see Dalton's digs at Manchester, but I think it's a Chinese restaurant. Or like the back of a Chinese restaurant or something. They didn't preserve it. But you can still see it. There's like a little plaque on the side and it said in 1808, this is where John Dalton lived. And you can go walk on John Dalton Street and you can go see a statue and the whole thing. But it's very cool. If you ever go to England and you want to do a sciencey, nerdy tour, just let me know. I'll tell you where to go. Okay. And in John Dalton's atomic theory, he had 3 basic principles. He said each element is composed of tiny indestructible particles. Those are the atoms. And, what was that? Atoms of an element are all exactly the same. Okay, so all exactly the same. It turns out this is not true. Atoms of an element can have some variation in them, like flavors of ice cream, right? There are different kinds of oxygen atoms. There's different kinds of mercury atoms. There's different kinds of carbon atoms. That's the one that's important for later. Okay. But when you have compounds or molecules, what it is it's a rearrangement of the atoms that are already in something else. Okay, so think about this. You have these things called atoms. They're not divisible. Those things make up every element. And if you rearrange the atoms of elements, you can get compounds. Yeah, that's kind of the idea. I'm going to skip a lot of the pretty stuff here. Sorry, this is IBM drawing with atoms. So, skip forward to the modern era, early 1900s. We're going to talk specifically about what is in atoms and skip a lot of the history that goes between, even though it's kind of interesting. There was a guy named J.J. Thomson, and he used what's called a cathode ray tube. So let me sketch out what a cathode ray tube is. It's very simple, actually. You take a negative electrode, and then a vacuum. You guys are funny. And a positive electrode. So this one's negative, and this one's positive. And then this isn't a, you guys stop laughing. And then you run an electric current through it. All right. We know what we're giggling about. And the beam would travel through the vacuum. You would generate a beam. It would glow. Okay? And then what he did is he put positive and negative electrodes on the sides. And the beam would move in different directions depending on which way you made the voltage go. So he could make this beam go up and down depending on what the voltage was. It's actually the precursor, the cathode ray tube is the precursor to the old television. So I always tell people, hey, look, great things came from TV, our understanding of electrons. Now, the fact that he could get these electrons to move towards a positive charge told them that they were negatively charged. One of the basic principles of physics, and we don't spend a lot of time talking about this, is that opposites do what? Attract. So if you can make a positive charge and negative charges are attracted, or something is attracted to it, you know whatever makes that thing up, right, is negatively charged. And so that's how he could tell that that beam was made up of negatively charged particles. Well, there's another thing that's generally true. All matter is electrically neutral overall. Okay? So matter, if matter is electrically neutral, and you have negative particles in matter, what else does there have to be? Positive particles. So this is the way Thomson came up with one of the very early experiments. He said, well, if I have negative charges and I have positive charges.
I'm so sorry. I got the giggles so bad. Okay. I'm good now.
Oh, good. I'm going to draw something else and see what happens. It's worth it. Although you're going to miss a lot of class. Every third drawing, I got to leave. This is why I got a degree in the sciences and not chemistry. Don't worry, I'm not offended by very much. So. As long as you're not mean to other people, I'm pretty cool with it. Okay, that's basically my philosophy. Oh, it's a whole love thing anyways. I could talk about it for a while. That was a good drawing though, wasn't it?
It was really good.
So anyways, what we're talking about is his theory. And he came and called it the plum pudding model. Says if you have negative charges in matter, you're going to have positive charges. And he thought, they're going to all kind of be spread out. Okay. He gets this student to work for him. His name is Rutherford. And Rutherford says, well, I guess I'm going to have to test this idea out. It turns out Thomson, this is the story I heard when I went to Cambridge. So my nerdy tour. He didn't really like him that much. Stuck him in a closet. Says, hey, you go do this experiment in this closet. So he goes in this closet to do this experiment, and he comes back to him, and this is the result that he gave him. And this is the experiment. It's called the gold foil experiment. So know this gold foil experiment. Know J.J. Thomson and the electron. Know the gold foil experiment. Thin piece of gold. Now the thing that's cool about gold is you can smash it and make it extremely, extremely thin. In fact, you can make it so thin you can hold it up to the light and you can see light go through it. Okay? You don't think about that, but you can make it as thin as one atom. Now he didn't know that at the time. But he makes the gold foil, he makes it extremely thin. And then he has what's called a source, okay, but the source is actually a piece of uranium or radioactive material. And what the radioactive material does when it decomposes is produces another particle that they knew about, known as the alpha particle. Okay, so this is like the alpha particle. That's like the gold foil. And I'm going to do this. Tell me what's going to happen. How many times will I do that until it goes through?
That would be really cool if it would have gone.
It goes through.
That would have been really slick.
right? So kind of several outcomes could happen from this experiment. He's taking these alpha particles. They're actually very massive particles as far as subatomic particles go. It's almost atomic, actually, but it's flying to this piece of gold foil, and it does this. Most of them go straight through. So it would have been, like, if this had really just gone through, you would have been all like, whoa.
Yeah, that would have.
That's just crazy. Well, that's kind of what Rutherford expected, because this particle's really big, okay? And Thomson really thought of first, but this particle's really big. It's going towards this gold foil, and the pieces that are in there, these pluses and minuses, are probably pretty small, and so it should just kind of go through. It can kind of just push its way through. The plum pudding is what he called it. So these particles should go like this, and they should just kind of go like this, and most of them should be here, and in fact, that's what happened. But here's the thing. About 0.1% of the particles flew straight back. Okay, so now, if I did this experiment, do a thought experiment. What was your name again? Rebecca. So Rebecca's standing here, and we're running towards each other. Okay, what's going to happen? If we're going the same speed, what's going to happen when we collide? We're going to bounce off each other. Now, who's going to bounce further? Probably her, right? Why? Because he's smaller, has less mass. I'm larger, and, you know, more massive. You saying I'm fat? I could have done it the other way, you know. I could have, yeah. You think I'm fat? Okay, so this particle runs into here, comes back. So the conclusion has to be this. Since the alpha particle bounced straight back, whatever it ran into had to be really heavy. Had to be really heavy for that to happen. And so the conclusion was, well, two things, okay? Two conclusions from this. Since most of the particles went straight through, like if I was throwing stuff at the wall and you saw it just going through the wall, what would you assume about the wall? There's a hole there, or it's not there really. It's empty. Like a hallucination or holograph, right? I don't think I can make you all hallucinate, but yeah, so that's the thing. Matter is mostly empty space. There's nothing there. It's kind of like if you think about the scale of the solar system, right? How many of you know this kind of like the general scale of the solar system? If the sun was this big, okay, like Neptune would be about a quarter of a mile away, and it would be this big. So think about all the space that's in there, right? The sun, this big, all empty space for a quarter of a mile, and then another planet.
Did you see the video that they replicated the sun as a marble? They did in the desert and they scaled it out.
Oh, really?
Yeah.
Yeah, it's kind of crazy video thing. We do it with an elementary school, the science club that I work with. We do that at elementary school, and we have a walnut, and we have a grain of rice, you know. We have people walk different distances. But yeah, what's amazing about that is as we look at space, which is actually empty, right? There's nothing in space other than some dust. There's very little matter in that space. Well, it turns out if you look at the atomic scale, it's the same thing. I have a nucleus, okay, what we're going to talk about in a second, and we have all this empty space. And we know there's a lot of empty space because 99.9% of the particles pass through.
Isn't that dark energy, though, or dark matter?
No, let's not go there. I don't know anything about dark matter, really.
No one does, though.
I know about darknet. Does that count? No. They're like, what? Never mind. I'm not looking you up on the weekends. Just trust me. So, okay, so most of matter is empty space, but what matter is there is very dense. Because you have to take all the mass of the substance and jam it into this little space because most of that space is empty. Okay, so he called that really dense region, he called it the nucleus. And that's where all the mass is. So when you think about space, or if you think about atoms, the concepts are generally the same. Okay? Matter is empty space. Mostly empty space. And that goes along with this observation that all the particles flew through. But a few particles deflected or came straight back at large angles. So what goes with this observation here I should say, what matter there is very dense. That matter that is in the nucleus is very dense. Oh, ran out of room. Very dense. And, you know, they come up with all these kinds of crazy analogies. Like if you took all the nuclear matter that you could fit in a teaspoon and like how much it would weigh like the same mass as like the Earth. If you got rid of all the empty space.
So the particles were deflecting off the nucleus?
Yeah, so they're deflecting off that really highly dense region, and he called it the nucleus. That's where we got the idea from. Okay. So these are the summaries. I'm just going to say it again. This is where you can read it. I just wrote it on the slide where the observation was so you could see it. Most of the atom's mass and all of its positive charge are in the nucleus. Most of the volume of the atom is empty space. Okay. And then we talked about this already. If you have to have neutral, negatives and positives have to balance. And it turns out, based on some other calculations that he did, that's where he got the idea that the nucleus had the positive charge. Okay. I'm going to skip over some of this. So what is in the nucleus? Well, it turns out when they try to add up the mass of atoms based on the positive charges and the negative charges, they try to figure out what's the total mass. It turned out there was always something missing. And it turns out that there was another subatomic particle that didn't get discovered till the early, like 1932, I think. And that particle was the neutron. So the discoverer of the neutron was a guy named James Chadwick. He is also one of Thomson's and Rutherford's protégés. So all this happened in Cambridge. That's why people go there to see, like, they still have all their equipment. You get to see all their equipment. So James Chadwick, this is a bit of trivia for you. About 1932, discovered the neutron. Now, here's the deal. The neutron was hard to discover because it turns out the neutron doesn't have charge. And the way they discovered the proton was by discovering the electron, and the electron they discovered because it had charge, and that was easy. So Chadwick came up with some pretty ingenious ways to find the neutron, okay? But why does that sound vaguely familiar? James discovered the neutron. Jimmy Neutron. So I just thought I'd tell you that. That's the naming of Jimmy Neutron. James Chadwick discovered the neutron. He never gets any glory until Jimmy Neutron came along. Okay, so here's the deal. The mass of a proton and a neutron are these, 10 to the minus 27 kilograms. You notice they're almost exactly the same. The difference is the subatomic particles that make them protons and neutrons, have different masses, and that's why they have different masses. Okay, we have a thing called the atomic mass unit. The atomic mass unit is so we don't have to write this number over and over and over again. A proton weighs about 1 atomic mass unit. The neutron weighs about 1 atomic mass unit. The proton's just a little bit lighter than the neutron. And the electron, this really small particle that Thomson discovered in his cathode ray tube that made somebody laugh a lot, this is all that it weighs. It's very tiny. It's about 1/1800th of the mass of a proton or a neutron. So in the nucleus, what you have, all the mass, and then it turns out the electrons are in essentially, and we're going to clarify this more later, in orbits around the nucleus. We call them orbitals. It's not orbits like you think of planets, but it's a space and volume in which they're contained around the nucleus. They don't just like go like, if you look at our solar system, everything's sort of in a plane except for a couple of oddballs, right? It's not like that, but they are in a region around the nucleus that we call an orbital. So here we go, protons and neutrons for all atoms, right, all atoms are neutrally charged. The number of protons equals the number of electrons. But the number of neutrons, it turns out, can vary. You can have variations in atoms just by changing the number of neutrons. Okay. Let me skip a couple of things here. Oh, this is kind of the scale. If the proton was a baseball, then an electron would be a grain of rice. It took a year to grow, as my grandmother would say. Yeah. Now, remember we talked about there being really high regions of density in matter that we call the nucleus? We don't see that because the scale is too small, right? So, like, when you try to push yourself, like, if you wanted to think about it, weirdly enough, there's so much empty space in matter, why can't you just walk through a wall, right? Because it's so densely spaced that you can't actually do that. There's too many connections between the atoms here and the atoms of you that you couldn't go through the wall. Okay. So we have a periodic table, and this is an important number. It's called the atomic number. The atomic number is the number of protons in the nucleus. It's usually given the symbol Z. I like to give the symbols because it makes things easy to manipulate later. And it's what makes an element an element. So if you look on the periodic table, okay, hydrogen has 1 proton. It's the smallest nuclear charge of the elements. Helium has 2. Lithium has 3. Guess where this is going? 4, 5, 6. The way the elements are arranged on the periodic table is by their atomic numbers. This number in the top right corner, it seems like, oh, they just use these numbers to keep it organized. That's actually the number of protons in the nucleus. Okay. Hydrogen has 1 proton. If it's electrically neutral, how many electrons does it have? 1, right? Hydrogen atom has 1 proton and 1 electron. Now, how many neutrons does it have? That doesn't come from there. Okay, it could have 1, it could have none, it could have 2. All right? Those are the common ones. But typically, it has just 1. But because the neutron is neutral, it doesn't affect the charge, it doesn't affect the electrons. And electrons are like your clothes, right? If you didn't have any clothes on, people would react to you in a funny way, right? So the electrons are the clothes. So the clothes all that matters is what's in the nucleus as far as positive charge. So the neutral charges don't matter. So how something reacts, right, depends on the neutrons, the electrons, and that depends on the protons. How many electrons does sulfur have? What's sulfur? S, yeah, number 16 here. So it's got 16 protons. How many electrons does the sulfur atom have? 16, right? It's going to be positives, and negatives are going to be the same. What about iodine? 53 protons and 53 electrons, okay? Same number. Radon, which we find in our basements, unfortunately, 86 and 86. This is for the atoms, okay? Barium, this is barium, 56 and 56. So it's fairly straightforward. Protons and electrons in an atom are always the same, and you can tell what it is just by looking on the periodic table. You get a periodic table on your test book. You don't have to memorize all that. Okay. Now I'm going to skip. This is a big periodic table. I'll come back to it if I need to. Well, actually, let me use this one part of it. So on this periodic table, which I think is the one from your book, but I'm not positive, right? You notice there's a box here. They've highlighted beryllium. It has a 4 at the top. So what does the 4 mean? Protons, right? Which is the same as electrons. The symbol is the Be, right? The atomic mass, how much it weighs, is an average mass. It's not just of one particular atom. But what they do is they go out and they get a lot of beryllium and they determine what the average mass is. Its average mass is written as atomic mass units. So an average sample of beryllium, the mass is 9.01 atomic mass units. How many atomic mass units is a proton? 1. There's 4 of them in there, right? So the average beryllium atom must have around, it has 9 total mass, must have around 5 neutrons floating around in its nucleus. That's the average, not each one, but an average of them. If you look at copper, right, this is kind of weird because it's 63.5, but that's because of the average, okay? Well, there's 29 protons, which is about 29 atomic mass units, but it has a mass of 63.5. So on average, how many neutrons on there? About 34.5. Right? So the number of neutrons changes, though. That's why that number is a half. Sometimes it's 60, I think it's 63, and sometimes it's 65, I think. Okay? As the total number of protons and neutrons. Okay, so we'll get back into that in a second. I already talked about the symbols already and the ones you have to memorize. There's just some examples on here. You'll notice some of the oddballs, though, they come from Latin or Greek, so potassium is the K. Also one of the hard ones to remember. Kalium. Sodium is also, unfortunately, one of the hard ones. It's Na, which is natrium. Okay. Lead is plumbus. Mercury is this. I can't even say it. I can say mercury, though. Iron is ferrum. Silver is argentum. Tin is stannum, and copper is cuprum. So that's where those symbols come from. But like I said, if some people in other countries, they still use those words, and they pick up on it real quick. Okay, but most of them are based on what we know in English. So most of them are pretty easy. Just like 4 or 5, you're going to have to just like make yourself learn. And the spellings. One of my pet peeves. Oh, yeah. The element of surprise. Never mind. All right, so you're going to have to find the name and atomic number for each. So let's do this. Na is what? Sodium. You guys are good. What's its atomic number? How do you know? 11. What's Ni? Yep, nickel. Atomic number? 28. Phosphorus, or P is phosphorus. I would have done that one. So, but what's its atomic number? 15. By the way, you'll see 2 different spellings for phosphorus with an OUS sometimes, and one's British and one's English, and I don't care which one you use. Oh, TA. What's TA? Where is it? 73. Talantinum. And honestly, I think I know them all. I don't know. Every once in a while I go through and go, what is that again? It takes me like a second to remember what they are. Okay, so we're talking a little bit about something called periodic law. There's a guy named Dmitri Mendeleev. Mendeleev said, hey, look what happens when I organize elements according to increasing relative mass. So what they did actually is they figured out, they didn't know atomic mass units at that time, so he figured out how much each element weighed relative to each other by doing chemical reactions and weighing things. And a lot of people were involved in this kind of research. But if you take hydrogen, helium, and lithium, and beryllium, the colors represent their reactivity and how they behave. Turns out with oxygen, he was making oxides. If you line these things up like this, increasing relative mass, and you just color code it, it's the easiest way to look at it. You notice it goes green, red, and orangish, right? Green, red, and oranges. And he noticed that the chemical properties repeated as you went through after you organized the elements this way. And so then he had this bright idea of, why don't I take, ignoring hydrogen and fluorine and all those things, take all these guys and line them up in columns like this. And that's actually where the structure of the modern periodic table comes from. So that lithium and sodium, potassium have a certain reactivity with water to form certain oxides that are all the same. Beryllium, magnesium, and calcium do the same thing. Fluorine, chlorine, helium, neon, and argon. Hydrogen was the oddball. Hydrogen could be over here by itself, or it could be over here. It turns out it has some of the same properties as both. So in a lot of the old periodic tables, you actually see it in two different places on the periodic table. Okay? Just because its reactivity is the same as the others. So why is it called the periodic table? Because properties repeat periodically. That's where the name for the periodic table of the elements comes from. Okay? And it had mostly to do with reactivity. So this is our modern periodic table. Oh, I wanted to mention one thing. So this is what he did it with, right? And he just organized it like this. And these ended up being called the main group elements because he grouped them together, so it's the main group, right? And unfortunately, the periodic table looks like this. Like, dang it, did all that work. What the heck's all this? Okay, so I'm going to have, these are things that you're going to need to know names of, okay? So, talked about the main groups. The main groups are also known as the A group. Now, on this periodic table, unfortunately, the A group doesn't show up because IUPAC, the group that organizes all this stuff, decided we don't need them anymore. But this is 1A, this is 2A. This turns out to be 3A. Fortunately, it's 13, so you can kind of remember that. 4, 5, 6, 7A, 8A. Those are the main group elements. Those are the kinds of things that Mendeleev was working with the most. Okay? Well, then all of a sudden, there's all these other elements. So what do you do with them? You give them a different name. These B elements, like let's say A team, B team, these are known as the transition elements because they're the transition from the left side to the right side. That's how they get their name. Okay, so transition elements. I'm going to write that on here. You mind if I just write right over the top of it? So all of this, and I'm going to use a, like this. And this is transition. All the B's. The A's, I'm trying to get the color to change a little bit more than that. That kind of looks like a different color. Those are the main group. Okay. Now you notice there's a lot of other colors on here. Guess what this is called? You notice what this is. This fits in here. There's 57, there's 58, and then all the way on through 71, and there's 72. So these guys have names, and you got to know those too. But these are known as the inner transition elements. Why? Because they are inside the transition elements. Okay. So this is inner transition. So I'll just write that. Oop, didn't get the inner transition. All right. Now, these have names too. This whole row here, okay, is called the lanthanides, and this one's called the actinides, but the names are on here. Now, along the vertical orientation here, where everything has similar chemical properties, those are known as groups or families. So let me make a little note here. It looks like this. This is groups. I like the old term families. Families. Why do you think they call them families? They're similar, yeah. So like my children, right, are my family. They all kind of look the same when they come out. But as they grow up, they kind of look the same, not as identical as when they come out. Do I have to explain that? No. So when they come out, they grow up, and as they grow up, they have very similar properties. They all kind of laugh at the same jokes. They all kind of do the same things, right? But they're all different too. And that's the same as it is here. These all have similar reactivities along this group or families, but they're each have their own identities, okay? Now, if you go left to right, this way, okay, that's known as a period. So, periodic table, period. The thing about periods is, as you go left to right on a period, chemical properties change, but they don't change suddenly. They change gradually, usually, as you go from left to right. And so there's actually a lot of trends, and we'll talk about those in later chapters, a lot of trends on the periodic table, like if you know what these two are doing, you can tell what this one's going to do without knowing it. In fact, some of the elements on the periodic table, like germanium, were not discovered, but they predicted its properties before they found it, and when they found it, that's how they knew they found it. They predicted its properties based on the neighboring elements. Okay, let's see. Groups, families, periods, transition elements, intertransition, main group. Okay, so there's other things that you need to know on here, and there's some of them are already highlighted. There's the metals. I'll have to write out the properties of metals, but you kind of know what metals are, right? What is a metal? Give me a property of a metal. Dense. Hard? No, they're actually, they can be hot, soft too. Yeah, okay, gold is soft, right? So there's a lot of variability in that. It's shiny, right? Conducts heat and electricity, right? So we'll talk about all this. One of the other ones is it's malleable. That is, you can shape it into a very fine foil and put it on things, make gold leaf, those kinds of things. It's also ductile. Ductile means you can draw it into a wire. It doesn't mean what's on the duct's floor, but you can draw it into a fine wire. Ductility, I suppose, is the word. Okay, but let me go back. So the metals are this light yellow color. What is most of the periodic table? Metals. Most of it's metals. Right? You don't often think as potassium or sodium being a metal. Now, the lab tech wasn't here today, so I wanted to take some sodium and cut it for you so you could see it, and some potassium and cut it for you so you could see it, and then we're going to throw it in water. So you can see how they react the same. We'll do that. We have to do it in lab because it generates a lot of fumes. But he wasn't here today, so I couldn't do it. Anyways, sodium and potassium are both metals. You don't think of them that way. Now, the nonmetals, okay, are just this little group here. But they're very important because you have in this area, you have carbon, which is essential for our life, right? Nitrogen, oxygen, phosphorus, and sulfur. These are all the things that make us, including hydrogen, which is a nonmetal, and it's the oddball that's up here. Then we have the metalloids. So one of the things about metals is they conduct electricity well. Nonmetals don't. Semi-metals, or often referred to metalloids, are kind of like metals and kind of not. It's what we get our semiconductors from. So the term semiconductor comes from the fact that the things that make it up are semi-metals. They don't conduct electricity well, but they you can actually turn the conductivity on and off depending on how you create a circuit out of it. And that's how all our computers work, is just a bunch of little wires that you can turn on and off. Okay?
Are all the nonmetals gases?
No, not all the nonmetals are gases, but many of them are. In fact, good question or good point. Nitrogen, oxygen, fluorine, chlorine, bromine. Sorry, not bromine. Nitrogen, oxygen, fluorine, chlorine, hydrogen, and then all of the noble gases are gases. Right? So if you want to, it's just from here to here and here. Those are all gases. Yeah, it's really fun to look at. I can look at it for a long time. Okay, so here are the properties of metals that you need to know. Okay, good conductors of heat and electricity, can be pounded into a flat sheet. So that's malleability. That is, you can squish it into any shape you want to. You can make wires out of it, ductility. It's shiny. The scientific term is lustrous, I guess. Now, here's something that you don't get from your common experience. They tend to lose electrons in chemical reactions. So remember I said atoms are neutrally charged, but when a metal reacts, it often loses an electron and becomes charged, and we call those ions. And we'll get more into that in a second. But iron, magnesium, chromium, sodium, those are all, from the periodic table on this side that we looked at already. I am going to take a break here. You guys need a break? Yeah. Let's do 10 minutes. So 10 till, come back, and we'll burn through the rest of the lecture. So we covered metals. Let's talk a little bit about nonmetals. I did mention some of these, so this is kind of like summary stuff. But some of the nonmetals are solid at room temperature. Others are gases. We just pointed that out. They're bad or poor conductors of heat and electricity. They tend to gain. This is, again, one of those things you wouldn't get from general observation. You have to do experiments. Metals would lose electrons. Nonmetals gain electrons. So guess what? When you take a metal and a nonmetal and put them together, one gives electrons to the other. And that's what we call a chemical reaction. It's the exchange of electrons and reorganizing of bonds. But that exchange of electrons is what we call a chemical reaction. And some examples. I'm not going to go into all the examples. We've talked about it already a little bit. Okay. The metalloids, that's that zigzag, sometimes called the semimetals. It's a mixture of properties. We call them the semiconductors because they have that intermediate electrical conductivity that can be turned on and off, can be changed and controlled. Means you can turn the conductivity on or turn it off or change it so it's somewhere in between. Okay. All right. So let's classify these. You got a periodic table over there. S, what is it? Non-metal, based on its position on the periodic table, right? This is definitely on the non-metal side. Chlorine, non-metal, that's over here, Cl. Titanium, metal. And if you were to classify it further, what would you call it? Transition metal, right, to add a little bit more description to it. If you're going to go into engineering, you're going to spend a lot of time working with the transition metals. A lot of structural materials are built from the transition metals. If you're also going to go into new technologies, you're going to need to learn a lot about carbon. A lot of the carbon fiber, graphene, nanotubule stuff, that's all carbon. Okay, to titanium, SB, antimony. Metalloid. Here, that graph there. All right. Okay. Skip. Okay, some of the groups have names. You have to know these names. And I'm going to add a name to this because if you're in geology or go into geology, there's another group you need to know. Okay. But the alkali and alkaline metals, earth metals, are here. Okay. They're both very reactive with water. I'll go over their properties in a second. I just want to show you where they are on the periodic table. And when we talk about making things alkaline, That means there's a term for that. It's called basic. There's basic and there's acidic, okay? When we talk about making things alkaline, when you add alkali or alkaline earth metals to water, the solution becomes alkaline. That's where they get that name from. Okay. Now, we have the halogens here, the chlorines, the fluorines, the bromines of the world. And then there's the noble gases. Now, the noble gases are kind of interesting. A professor named Ramsay in England at University College London discovered a lot of them. In fact, I think, if I'm not mistaken, I think his son, he let his son name Argon. Means the lazy one. Okay, so the reason they named argon the lazy one is whenever you took air, you can take regular, like breathing air, and you can extract and react all the oxygen out of it. That's really easy. And then you can react the nitrogen out of it, and that's pretty easy. And then there's always this like 5% left that you can never get out. You can't react it, you can't do anything with it, because it's completely unreactive. So they called it argon, the lazy one, because they couldn't get it to react, so they couldn't figure out what it was. So it happened to be this. So it gets the name, this group is all like that. Helium, neon, argon, krypton, xenon, radon are all relatively unreactive. So they call them the noble gases because they don't mix with the other common elements, right?
Isn't helium finite?
What's that?
Isn't helium like limited? It's finite?
Yeah, so helium is a kind of a problem right now because we get our helium from the ground. It is a byproduct of petroleum mining, or I don't know what you want to call it now these days, but from getting out of the ground. So it comes from those wells. Eventually that will run out. And the thing about helium, what do we use helium for? Balloons and make your voice sound funny, right? Well, because it is so much less dense than air, turns out, it just floats into the upper atmosphere, so it goes away. So eventually, after we make all these helium balloons, we're going to lose all the helium to the upper atmosphere, and so we won't have things like helium balloons. And it turns out it's really useful in a lot of instrumentation. It's just going to disappear.
Is it true that if you're really super deep below water, like in those things, submarines, you
Yeah.
have to breathe helium
Yeah.
instead of...
Okay, so you don't breathe helium. So just a little side note. Oxygen is the gas that you're breathing, okay? Is O2, so we would write it like that. It's about, now, you don't know this unit yet, but there's a unit called an atmosphere. 1 atmosphere is what you're in right now. You don't feel it, but it's 1 atmosphere. Okay. It's about 0.2 of the atmosphere that you're breathing. And it needs to be that concentration because when it goes into your body, it bonds to hemoglobin, right? And then on the hemoglobin, it gets transferred to cells, okay? And that's how you get your oxygen to your cells. Now, if you increase the pressure beyond 0.2 atmospheres, then what happens, you get too much oxygen. You can actually kill your cells by having too much oxygen. You guys know that song from the 70s, Love is Like Oxygen? No? Yeah, the next line is something, something, and then too much you die. Right? Because they caught on to this idea, if you get too much oxygen, you're going to die. So to avoid that problem, when you go really deep, right, and you're at the bottom of the ocean, the pressure is really high, it turns out this will also increase because the pressure's high. So what they do is they mix in helium to keep this at 0.2 atmospheres. Now, if you came up from down deep and you still were breathing this mixture, you would essentially suffocate. There's not enough oxygen for you to get into your system, right? Yeah, so yeah, it is true. When you go down deep, you have to have some helium in the mixture. It also gets out of your, it leaves the, so oxygen is dissolved in your blood, nitrogen is, and the helium is. When you decompress, the helium leaves nicer than some other gases do. So like if it's nitrogen and it leaves the solution, what does it do? It forms bubbles in your blood vessels, and that's called the bends, right? So you try to avoid that. So helium is nice about that too, apparently. Whatever nice means. Okay, let's look at group 1. Group 1, alkali metals, right? They're very reactive. That's what lithium looks like. This is what sodium looks like when you throw it in water, so that's kind of what I'm hoping we're going to be able to do tomorrow, right? Turns out, as you go further down the periodic table, it gets more and more reactive. These ones down here will literally explode as soon as they hit the water. So we don't do that. But you can go on YouTube and look it up, really. Okay. Alkaline earth metals are a little more reactive. So you don't think about calcium being a metal, but calcium is a metal, right? This is calcium going actually into an acidic solution, so we're kind of cheating here. It doesn't bubble like that normally, but that's calcium reacting with water. It's actually producing hydrogen gas. Okay? And magnesium is another fun one. Magnesium, anybody ever play with sparklers? Right? You're all people, right? You play with sparklers, right? The bright white flame is magnesium burning. Used to make VW bug engine blocks out of magnesium until they caught on fire and they realized, wow, this is really hard to put out. It's like 5,000 degrees. This is like crazy hot. They used to light them on fire and push them into the ocean. I don't know, that's what people do at the beach. Okay. And the crazy thing, it burns hotter with carbon dioxide. So when you take a carbon dioxide extinguisher and you try to put it out, bad idea. Yeah. All right, so halogens, that's group 7. Here's some examples of the halogens. This is a neat group because the top of the group is gases. The bottom of the group is solids. Now, this acetate, we don't really know much about it. There's only a few grams we predict to be in the Earth. Right? So we don't get a lot of this to like play with. But fluorine's a gas, chlorine's a gas, it's a yellow gas, bromine is actually a brown liquid. And iodine makes beautiful crystals, iodine crystals, and they're all poisonous, by the way. It's really fun to look at. I play with them at work all the time. But the noble gases, right, are chemically inert, mostly chemically inert. Krypton and xenon we can make stuff out of. One of the cool things that you can do with all the noble gases, though, is if you run an electric voltage, a current through them, you can make them emit light in the visible spectrum. And that means you can see it. And that's where we get neon signs from. But you can actually make signs out of helium and argon and krypton as well. They're just different colors. So let's, there's the one more. I wanted to point out one more group, and I'll just point it out over here. It's the group headed up by oxygen. So oxygen's group, and I'm going to write it on a separate sheet here real quick. So this is actually group 6. Group 16, or 6A, or Roman numerals 6A. Okay. These are known as the chalcogens. And chalcogens are oxygen-containing minerals. So we find chalcogens in the ground all the time. So if you're a geologist, you may see this term chalcogen periodically, and you will see them as oxides of different, like, metals. Okay. All right, so let's classify some of these. So lithium is a metal, family, element. What family does it belong to? Alkali metals, right? And then boron. Oh, we didn't do boron. Yeah, I guess in the metalloids. Would fall in the metalloids. It's group 3A would be the metalloids, though. What about iodine? Non-metal, and what group name? Halogens, right? And argon?
That's a gas.
Noble gas, yeah. So part of this is, you see, you can get asked these, they're not hard questions. You just have to kind of know what all the groups are and then be able to find it on the periodic table. I might ask you, what's the element in group 3A on the 4th period? All right, what's the element on group 3A? So this periodic table doesn't have, but this is 3A. The fourth period is starting here. That's they helped you. They put the 4 there. So you go all the way here. It's gallium, right? Gallium's cool because it melts just above room temperature. Usually you stick it in your hand and it'll melt in your hand. It's also toxic, but you can still wear a glove and do it. Indium is cool because if you take a piece of glass, it also melts around room temperature. You can stick glass in it and it sticks to the glass. Makes like mirror coatings on the glass. I played with that too. So now we're in the home stretch here. If an atom loses electrons, okay, what kind of elements lose electrons? What group, what classification of elements generally lose? Metals lose electrons, right? They become cations. They have a positive charge. Okay, so let's do this. If sodium becomes a cation, it usually forms this. You would write it like that. The element symbol with the charge next to it. Well, because it has a +1 charge, how many electrons did it have to lose? Just 1. Calcium, right, is also a cation. Usually makes a 2+ charge. How many electrons did it have to lose? 2, right? Where, if you look on the periodic table, where's sodium? What group is it in? Alkali metals in group 1. Where's calcium? It's in the alkaline earths. It's in group 2. It's not a coincidence. It's in group 1, and it generally makes +1 ions. Everything in group 1 makes +1 ions. So if I ask you what ion lithium makes, right, it generally tends to lose 1 electron, and it becomes a +1 ion. If I ask you what ion magnesium makes or strontium makes, right, it's in group 2, it tends to lose 2 electrons. Okay? So it makes a +2 ion. So metals tend to lose electrons, and it turns out you can predict what the charge is going to be just by looking at where it is on the periodic table. Okay? Now, if you have a hard time remembering cation and anion, which most people don't, I always remember the cation has a little positive charge right in the middle. The T, that's my positive charge of my cation. Okay? Anion, an is the prefix for not or negative, and so that's where we get the term negative ion. Things that are negative ions are generally what kind of elements? In the nonmetals, right? So the nonmetals tend to pick up electrons. Now, if I'm fluorine, it turns out fluorine tends to pick up 1 electron. So what's its charge? -1, like this. Okay. And turns out phosphorus, I tend to pick up 3 electrons. So what's my charge going to be? -3. So phosphorus would be P, all right, 3 minus, like that. Yeah? Yeah, there is a trick to it. She already picked up on it. So on this side, you tend to gain 1, right, from here. But why is it special that fluorine picks up 1? Well, if it picks up 1, it has 10 electrons, just like neon. You remember, these were really unreactive, right? So that's why it will gain 1 until it gets to here, and then it stops. If you're phosphorus and you pick up 3 electrons, right? You have 15 now, you get 3 electrons. How many electrons will you have? 18. You'll be like this. Now, look at potassium. When it loses an electron and becomes +1, how many electrons will it have? 18. It'll be like this. So a lot of this behavior on the periodic table is just driven by how close they are to the noble gases. So you can remember, starting from here, -1, -2, -3. And this one is +1, +2. These are actually +3. It turns out the reason these are 3A is because these tend to make +3 as well. Okay? So you can predict just based on distance from She's like, wow, you're a genius. The distance from the noble gases, not me, she's telling her.
No, I told her you just got me confused.
What? What did I say?
No, because isn't it on the
Yeah, that's where things, so you're going to react until you're stable, right? So you're going to eat until you're full. So these guys are eating. Well, these guys are pretty close to this, so they're only going to eat 1 electron, and these guys will eat 2 electrons, and these guys will eat 3. Now, this is gross, okay? These guys ate too much. So they're going to, they're going to throw up. These guys will throw up 2 because they got to get rid of 2 to become like a noble gas and be sleek and slender like this guy over here. Sorry, I don't mean to pick on you, but you seem like the type that would be okay with that, yeah. Yeah. That makes sense? Everything's kind of driven by where the noble gases are. But it turns out these ones also will be +3. Okay, so we put the element symbol and we show the charge in the upper right side. The magnitude is determined by the distance from the noble gas. Okay? Now, where was I at? I get sidetracked a lot.
Does a cation and anion have anything to do with like a cathode and anode? Is that
Yes,
the
because a cathode is negative and an anode is, well, it depends on what you're doing. It can be positive, negative, depends on if it's a battery or a hydrogen generator. The voltage sign changes. But anyway, I'll talk about it.
Oh, that's okay.
We'll go over some other time.
All right.
Okay. So here's an example of a reaction. I've written a reaction. The reactant's lithium metal. I make a lithium ion. It loses 1 electron, right? I don't like the little math that goes on down here. You guys get the idea. If it loses an electron, it's +1, right? You don't have to do all this. Okay. Now, if I said I have let's say I have a sulfur ion. Okay. What's sulfur's ion going to be? Sulfur's here. It's S, but it's going to be 2 what? Positive or negative? Negative, because it's going to gain, right? So let me write a little note here. Sulfur, going to add 2 electrons to it. You'll make S2 minus. Now, how many protons does sulfur have? 16, right? How many electrons does the sulfur atom have? 16. And how many electrons does the sulfur ion have? 18, because it picked up 2. Okay? So if you're -2 charge and you started with 16, then you end up with 18. Okay? That's actually what those equations are trying to show, and it just gets a little confusing, I think. That's just from the book. Okay, so what we're going to do is we're going to try to do some charges based on an element symbol and the number of electrons, okay? So nickel. Oops. Nickel has how many protons? 28. So if nickel has 28 protons. What is the charge of a nickel ion with 26 electrons? +2. Because this is protons positive, right? It's got 26 electrons that are negative. So overall, when you add that together, it's +2. So that's nickel. If you wrote the symbol out, would be nickel 2+. Let's do bromide ion. Actually, you know the answer already, but that's okay. We're going to just do the problem anyways. Because it doesn't always come out pretty like this. Do you mind if I write on there and talk back here? Does that make you crazy? No. Kind of weird, I know. I might walk up to you and say, here, write something real quick. Okay, so bromine, 35. I'll just write it down here. That's the P plus. Now normally it has 35 electrons. Now it's got how many? 36. So what's its charge? -1, yeah. Ooh, you're all chemists already. Oh, don't say that out loud. It confuses everyone. She said it seems backward. I'll explain to you what she's talking about. I hope I don't confuse people. So the symbol is Br minus. Okay. Phosphorus. Phosphorus is where? P, right? So it's 15. So it's got 15 protons. How many electrons does it have? It says up there. It normally has 15, right? How many does it say it have up there? 18 negatives, right? So it picked up 3 electrons. Its charge is going to be 3 negative, yeah? Here's why people get confused. They say, well, you picked up something, and why are you negative? Because the thing you picked up was negative. That's what confuses people, right? You're picking up something with a negative charge, so your charge becomes negative.
So you're adding the minus.
Yeah, you're adding minuses. And then when you're losing them, you're subtracting minuses, and so you're positives, right?
Because it's the electrons that you're losing and gaining.
Yeah, because it's the electron has a negative charge. That's what's confusing about it.
So it's not,
The universe did.
That's not a better way.
No.
It's just changing the balance of the proton.
But if you come up with a better way, I think you could do it. Then yeah, you work on that. Okay, let's do protons and electrons and S2 minus. Go ahead and work a little bit backwards. What's S? Sulfur. Oops, I did it again. So sulfur has how many protons? So S2 minus had to have picked up 2 negative charges, right? So it has to have 18 electrons.
So technically it would be like negative 16.
I don't know why I did it.
Alright, when you're adding negative.
Hang on. I wrote that funny. I wanted to write, I wanted to write 16 proton pluses like that. Say that again?
I was just saying, so the number on top, like, if it's 16 and we're going to 18, it's almost like negative 16 plus than negative 2.
Yeah. You're thinking about electrons, even though there's protons and electrons. All right.
The transition metals in the middle, like if you were to make it
Okay, so let's say I have copper and it's got 27. Let's just do one. Copper. To keep consistent, let's say it's copper 2 plus. Now here's the thing about transition metals. Because of where they're at in the periodic table, they can often have different charges. So sometimes it's +1, turns out. Sometimes copper is +2, and very rarely is it +3. But usually 1 and 2 is what we see. What you see in, like, they use copper to treat water with too much algae in it, that's copper 2 plus. It retards the growth of algae and kills it. Okay, so, and it's also blue, which is really cool. You know, blue water, right, that kills you. Never mind. Copper 2 plus, I want to figure out protons and electrons, right? So how many protons does it have? 29. So how many electrons does it have? Well, it's supposed to have 29, but must have lost 2 to be positive. Right? So 27 electrons. So you can do it for all of them. But for the transition metals, I can't just ask you, what charge do you think it will be? Because it could be a number of different ones. I'd have to give you a problem like I just wrote here, copper 2 plus, protons and electrons. Okay? Okay. I'm going to skip over some of this because I talked about it already. Okay. These we called the fixed charged. This gets to what you kind of just asked about transition metals. Which elements can we predict the charges of? And for sure, these are the ones that we can predict, it turns out. We can usually predict that these are +1, these are +2, these are +3, and these are -1 and -2. Okay? Turns out these are generally -3, and this, if it makes it, is -4. But the ones you can always know when you see them in a compound, that's what their charges are based on the periodic table. So we often refer to these as the fixed charge elements, or fixed charged ions. But it turns out like these are also +3. I don't know why they're not. This is what the book tells you. So based on like that, that's what your homework is based on. I don't want to give you a whole bunch of other ones, but there's a whole bunch of them that you can predict from the periodic table. Okay, I'm going to skip over this because we've done it. Okay, isotopes. What time does this class end?
2:30.
Ah, man, 10 minutes to finish this. Okay. Doesn't add up. My calculator. So, isotopes. That was a nerd joke. So, okay, I know all these backstories. There's an instrument called a mass spectrometer. And in the early times of atomic theory, early 1900s, one of Rutherford students got assigned this job to make an instrument that determined how much each atom of an element weighed. And before this time, they didn't know that they were going to get, they thought they were just going to get one number. Well, when he took neon, actually neon's what he did it with, and ran it through this mass spectrometer, what he found out was that some of the neon atoms, right, most of them, had an atomic mass of 20, then some of them had an atomic mass of 22, and a fewer, even number of them, had an atomic mass of 21. And they're like, well, what gives? Why are neon atoms different? And this goes against what Dalton said. Dalton said all the atoms of an element are the same. And then they come along and they do this experiment, and what they find out is not all the atoms of an element are the same. Okay? And they also knew about neutrons, so the speculation then is what makes these different is the number of neutrons in the nucleus. So that's what they're seeing. And we get it through an instrument called a mass spectrometer. Okay, so if neon is neon 21 down here, I'm going to write it bigger so you can see it. 21 is known as the mass number. Because that's about how much it weighs in atomic mass units. Okay? How many protons does neon have? 10. All right? How did he get that so fast? He looked at the periodic table. That means there's 11 mass units, right, extra. Those are the neutrons. So the mass number reflects protons. It usually gets the symbol A. And A is protons plus neutrons. If that's equal to 21, right, and the protons is equal to 10, N has to be 11. There's 11 neutrons in that N. If there's 11 in this one, there's 12 in that one, and there's 10 in that one. Right? You just can do the math just thinking about 10 protons. 10 plus what makes 21? That's 11. 10 plus something makes 22. That's 12. Okay? I'll formalize this a little bit better. Of course, I'm not going to finish all the homework again, so we're going to have to push the due date back again, but it's okay as long as you stay up with it. Okay, so we can write, oh, sorry. So these got to be known as isotopes of an element. So they all represent neon because they have the same number of electrons on the outside, same number of protons on the inside, but they're different by their mass. It's kind of like flavors of ice cream, right? All right, it's all ice cream. They're just sort of different flavors of it. I think coffee's my favorite, but what you do is you write the chemical symbol, okay? And then when you're writing the symbol for isotopes, you have the chemical symbol, you have the atomic number, which we get off the periodic table, and then you get the mass number, which you calculate based, right, on the number of neutrons. You have to know the number of neutrons, or you have to have the mass number to figure out the number of neutrons. But you can't do one without the other. Okay? So what I wrote over here, this is one acceptable way to write it, actually neon 21, neon 22, and neon 20. The other acceptable way to write it is like this. And these are often called nuclide symbols. And it's how you express different isotopes of an element. All right. Let's see. Do one problem here. Maybe two. Yeah, we'll do two. All right. What is the atomic number, mass number, and symbol for the chlorine isotope with 18 neutrons? So, to do the symbol, we're going to have, remember, it looks like this. It looks like with the Z at the bottom left and the A on the top left. Okay? So, chlorine is what? Cl. The atomic number is 17, right? Somebody said it. That goes here. What's A? It's 17 plus 18. A is protons plus neutrons. That's 17 plus 18. That's 35. That goes up here. Like that. There's actually two flavors of chlorine ice cream. There's 35 and 37. Oh, sorry, isotopes of chlorine. It's not chlorine ice cream. I'm using ice cream now to be isotopes. You're all like, what? I only know that because I've seen it so many times. There's two isotopes of bromine, too. All right, how many protons and neutrons are in the isotope potassium-39 is how we would say that. Hang on. Yes. So, K, 39, and 19. Okay, this is how I like to do it. Remember, this number is protons plus neutrons, right? This number is protons, right? It's 20. I just use it to do my math, right? So if I subtract the protons from the mass number, this is the number of neutrons. Now, if it's the potassium isotope, how many electrons does it have? It's not part of the question. But how many electrons would it have? 19. Now, if it was what about the potassium ion? It would be +1 charge, right? Because it's in group 1. So if you were to do this same problem with the potassium ion, it would be 20 neutrons, right? 19 protons and 18 electrons. Okay? So you would have to interpret that from the question if it's the ion or if it's the atom or the isotope. Atom and isotope you treat the same. Okay? But if it says ion, then you have to figure out is it going to be a cation, an anion, how many electrons does it lose? Okay. So potassium ion, let's do that one real quick. I'll just write it out. So it was potassium 39 ion. So it was K 39, 19, and plus, right? Then you would have come up with 20. So 20 neutrons, 19 protons, and 18 electrons. All right. That is exactly where I wanted to stop. Good.